So welcome everybody. Tonight we are privileged to have one of our distinguished fellows giving us a very special presentation on the Square Kilometre Array, which is something very close to my heart. So a warm welcome. My name is Anne Green and I'm honoured to be the chair of the New South Wales division of ATSI. And to begin, because this is now a separate session, I would like to acknowledge the traditional custodians of country throughout Australia. We pay our respects to their elders past and present and extend that respect to any Aboriginal and Torres Strait Islanders here today. As we meet on this land, I acknowledge the most ancient and enduring knowledge in the world embedded forever in custodianship of country. So tonight, as I said, we are privileged to have Sarah Pearce, Dr. Sarah Pearce, speaking to us. Sarah is director of the Square Kilometre Array Low telescope, soon to be built in Western Australia. And before her role with the SKA, Sarah was deputy director of space and astronomy at CSIRO in Sydney, where she established the CSIRO space program. She also spent 6 months in early 2021 as CSIRO's acting chief scientist. Her previous roles include providing science advice to the UK Parliament and managing large-scale computing for particle physics. She has a PhD from the University of Leicester and an undergraduate degree from the University of Oxford. In 2020, Sarah was named New South Wales Businesswoman of the Year and Executive of the Year at the Australian Space Awards. She was elected a Fellow of ATSI in 2020, and we're very pleased to welcome her to our division committee. So Sarah's talk is entitled Expanding Horizons for Radio-astronomy, the SKA Observatory in Australia. So the Square Kilometre Array Observatory will be built as the next generation of radio telescopes, transforming our understanding of the universe and the laws of fundamental physics. Tonight, Sarah will explore the science case for this international mega science facility, the technologies needed to deliver the next step for radio astronomy, and the opportunities that this amazing thing will bring to Australia. So welcome, Sarah. Delighted for you to take the virtual podium.
Thank you very much, Anne, and for that very warm introduction. So I'd also like to start by acknowledging the traditional owners of the land that I'm on today, the Wangal people, and pay my respects to their elders past and present. I also acknowledge the Wurundjeri Yamaji people of Western Australia, on whose land the Square Kilometre Array will be built. So I'm here to talk today about Australia's first mega science project, the SKA. This is a $2 billion international project, which will build the next generation of radio telescopes, one in Australia and one in South Africa, with headquarters in the UK. And it's Australia's first opportunity to host one of these billion-dollar instruments on behalf of the international community, putting us on the map alongside other world-class facilities like CERN, the Particle Physics Lab, or ITER for nuclear fusion. But I'll start by letting some of the worldwide team involved in the project tell you about some of its questions as an introduction.
What did the universe look like when the first galaxies formed?
What are gravitational waves? How does magnetism work throughout the universe?
Come si formano I pianeti?
How many gravitational waves are passing through me right now?
What is dark matter?
What is the impact of magnetic fields on the formation of galaxies?
宇宙の歴史はどうだったか?
¿Estaba Einstein en lo correcto?
And for me, the most important is there life out there?
We ask ourselves, what is the most useful thing that a radio telescope can contribute to the answers to these big questions? We are building a time machine. We're looking at what our surroundings were like almost at their inception. Question is, how are we actually going to make this happen?
Now, it's a very exciting time for astronomy, especially in the next few months. The SKA will sit alongside other powerful telescopes that are planned, letting the astronomy community study the universe at a whole range of wavelengths. So SKA will be complementary to instruments like the James Webb Space Telescope, which will look in the infrared with its amazing honeycomb set of mirrors and will be launched next in December. And on the ground, In the optical wavelengths, we're entering the era of extremely large telescopes with composite mirrors measuring several meters in diameter. So each of these facilities will give us a window on the universe and help us put together a piece of the puzzle. And the SKA will be the next great set of telescopes to fill in the radio part of that puzzle. Radio astronomy is a relatively recent branch of astronomy, and some of the very first radio astronomy observations were taken in Sydney in 1945 by scientists from CSIRO, as it was then, including Joseph Pawsey and Ruby Payne Scott. And of course, Australia's built on this history with world-leading instruments like CSIRO's Parkes telescope and more recently its ASKA telescope. So why is the radio spectrum so useful for astronomy? Well, most of the universe is made of hydrogen, and that hydrogen emits radiation at a specific frequency, 1420 megahertz, which is 21 centimeters in wavelength and slap bang in the radio part of the spectrum. So we can use this to map the hydrogen in the universe. And because radio waves pass straight through the dust that dims observations in other wavelengths, we can see things that you can't see otherwise. But in order to build a modern radio telescope, we make use of a technique called aperture synthesis. Essentially, an array of many antennas is used together to create a virtual giant antenna. So this animation shows how the separation of the antennas gives us resolving power. The further apart our antennas are, the more detail we can see. And then the more antennas we have in the array, the more photons we can collect and the fainter we'll be able to see. So we can use this type of array to tackle a wide range of science goals. And I'll just talk about a couple of SKA's headline science questions, starting with a key science area for SKA in Australia. What did the universe look like when the first galaxies formed? The Planck telescope was made famous by mapping the cosmic microwave background, or CMB, in an exquisite detail. That's a snapshot of what the universe looked like 380,000 years after the Big Bang. But what happens after that is still a mystery. We call this time in the universe's development the Dark Ages. And for around 150 to 400 million years, gravity pulled matter together in ever denser clumps until eventually the first stars formed and then the first galaxies. This is called the epoch of reionization. And we hope that for the first time with the SKA in Australia, we will be able to map this era and see what the universe looked like at that very first time, that cosmic dawn. The SKA will also be a great pulsar detection machine. Pulsars are very fast spinning neutron stars, dead stars, essentially. And they emit beams of radio light from their magnetic poles. If these beams are aligned with us, when they spin past, we see regular blips, kind of like a cosmic lighthouse. And they're pretty extreme objects. In particular, we can use them to test gravitational waves. By timing these pulsars really precisely, we can aim to see the ripples in the space-time caused by gravitational waves as they go past and complement the amazing discoveries of instruments like LIGO. Another of astronomy's ongoing mysteries is that galaxies and the universe are mostly made up of stuff we can't see, dark matter and dark energy. And together these account for about 95% of the total energy budget of the universe. SKA will study galaxy evolution in order to try and address this. When the full SKA is deployed, we'll aim to conduct the most complete galaxy census ever conducted, covering 12.5 billion years of the universe's history. And from this data, astronomers will be able to make the most precise determination of properties of dark energy and how this drives the expansion of the universe. And then, as mentioned in the video earlier, there's the eternal question of whether we're alone in the universe and whether it's possible to detect the presence of technologically advanced civilizations elsewhere in our galaxy. SETI, the search for extraterrestrial intelligence. When fully deployed, the SKA will be able to detect TV signals if they exist in our nearest stars, and airport radars tens to hundreds of light years away. So answering some of those really deepest questions potentially. But building telescopes on this scale needs really worldwide collaboration. SKA is an international partnership of 16 countries, and you can see the flags along the bottom there. It's recently been established as an intergovernmental organization. So that means it's set up with treaties between member countries, like CERN or the European Space Agency. And here you can see Australia's ambassador to Italy signing the SKA Treaty on behalf of Australia in Rome in 2019. So it was a very exciting day. And so there are 7 current members of the intergovernmental organization, and the other countries who are involved are all working towards joining. SKA is a great example of science diplomacy. It includes countries like China and India, and we're really building bridges between nations and cultures and encouraging dialogue and cooperation between governments, with results that hopefully will influence policy well beyond astronomy. So what are we actually building? Well, work by thousands of people over 20 years has been leading up to this. 2 telescopes, one in South Africa and one in Australia, in 2 very remote regions. In South Africa, in the Karoo, 600 kilometers north of Cape Town, and in the Murchison Shire in Australia, so that's 800 kilometers north of Perth. In South Africa, SKA will have close to 200 15-meter dishes spread over more than 100 kilometers. These will cover the mid-range of the radio spectrum, so 350 megahertz to 14 gig. And in Australia, our low-frequency telescope will see 130,000 antennas spread across the West Australian desert in clusters of 256 antennas each. There'll be 512 of these stations in 3 giant spiral arms from a very dense core spreading across 65 kilometers of the desert. And here you can see artists' impressions of the 2 very different types of antennas we need for SKA. The more traditional dish antennas in South Africa for mid-frequency radio astronomy, and then dipoles, kind of like large Christmas tree TV antennas in Australia to detect low-frequency radio waves. Both telescopes are real game changers in terms of capability. So here's the comparison between the SKA telescopes and the current state of the art in low frequency and mid frequency. These aren't incremental changes. They're skipping like a whole generation of telescopes. And the images show you just how much better the SKA will be able to see than what we can see now. On the engineering front, 12 international consortia have been working over nearly 10 years, bringing together 100 of the world's top institutes and companies to design the telescope based on requirements set by the astronomers. And each of the site already has Pathfinder telescopes on site, delivering outstanding science, but also demonstrating promising new technologies and providing insight into local conditions. So this is South Africa, the South African site, which has a Meerkat array of 64 dishes already producing great science. And this is CSIRO's ASCAP telescope in the Murchison Radio-Astronomy Observatory, what will be the SKA site in Western Australia. 36 antennas, each with innovative phased array feed radio cameras that let astronomers survey the sky much more quickly than ever before. So last year, ASCAP announced that it mapped 3 million galaxies in just 2 weeks, 1 million of those never seen before in the radio. And this is the Murchison Wide Field Array, a low frequency precursor in the Murchison, in the MRO, the Murchison Radio Astronomy Observatory in WA. It has more than 4,000 spider-like antennas. You can see them there, and developed by an international consortium. It's run by Curtin University. And the MWA is teaching us an enormous amount about both engineering and science for the SKA, a real precursor for the SKA-Low telescope. So in the last couple of years, we've seen a lot of progress to manufacture, install, and test future antennas for the SKA. So as you can see here on the screen, in the top, we've got the antennas for SKA, test antennas for SKA-Mid being made in China. And in the bottom, we've got test antennas for SKA-Low being deployed in Western Australia. In fact, one of the key aspects of SKA is that we're working with the best teams from all over the world to provide parts of each telescope and then bring them to the site. So the low frequency antennas will come from Italy and the UK, while the software to operate the telescopes is being led by India. And in Australia, we're doing a range of work from very high-tech signal processing through to building roads on site and then integrating the whole telescope. So it's been a really exciting time for SKA recently. So the treaty organization formally came into force in January. And then in July, the SKA Council approved the start of the construction phase. So that started on the 1st of July this year. So early next year, we'll see shovels on the ground in Western Australia as we move towards 8 years of telescope construction in both countries. And the telescopes will be constructed in phases in both countries. And you can see from this that there will be 4 or 4.5 phases of what we call array assemblies in Australia, starting with just deploying just a few stations and testing those, and then working up, of course, to deploying the whole array and being ready for the end of construction in about 2029. So I wanted to tell you a little bit more about the SKA site in Australia, CSIRO's Murchison Radio-Astronomy Observatory. So it's in the Murchison region of WA, as given away by the name. But the first thing to know is that it's incredibly remote, 350 kilometres from the nearest town of Geraldton. The Murchison area is around the size of the Netherlands, but has a population of only a bit over 100 people. So why are we somewhere so remote? Well, to get away from the artificially generated interference that all our computers and our mobile phones and our Wi-Fi and our microwaves and our cars make all the time, and that swamp the really faint signals we're trying to receive from the sky. So we have to get away from people to be able to do the best science. It might seem a bit odd that radio astronomers who were part of invention of Wi-Fi now want to avoid it, but here we are. We also have to make sure that the noise from our own equipment doesn't drown out what we're trying to detect. So even the buildings that we have on site will need to be very highly radio shielded, and staff accommodation will be tens of kilometers from the telescope to minimize that interference. And you can see here the control building for the ASCAP telescope, which again is a very highly shielded, high-tech building, even though it looks somewhat plain from the outside. Of course, being in a remote area brings its own challenges, and one of these is power. So ASCAP has a solar hybrid power station, which when it was built included Australia's largest battery. And it's also radio shielded and placed far away from the telescope in order to protect the telescope from any RFI that we might have. SKAO is also committed to sustainability in our power production. We'll be a responsible global citizen. And we know that power consumption for telescopes and computers is both our largest operational cost and our largest contribution to greenhouse gas emissions. So our design, we've aimed for low power hardware where possible, and we'll look for a high penetration of renewables in all our power supplies. Of course, for us, local engagement is also critical, and the Murchison Radio Astronomy Observatory is on the traditional lands of the Wurundjeri Yamaji people, and there will be an Indigenous land use agreement, or an ALUA, to allow us to build the SKA. So negotiated between the Commonwealth and the traditional owners, the ALUA will help the Wurundjeri see benefits from the SKA, such as contracts and jobs, and as you can see here, make sure that they get recognition from their ownership of the land. And then finally, I just wanted to talk about the data challenge for SKA. SKA is a big data telescope, producing as much data per second as 100,000 home broadband connections. So we digitize the signals as they're received at the antennas and then transmit those to central processing facilities over a total of 100,000 kilometers of dedicated fiber. That's enough to get us a quarter of the way to the moon, and it carries 8 terabits of data a second. into the central processing facilities. There, the signals are combined using FPGAs and GPUs. But first it is, first it is realigned. So the radio signals reach the antennas at different times, but we know the exact time the signal was received down to the nanoseconds, so we can account for that. The SKA will be able to distinguish 65,000 different radio frequencies simultaneously. So that's 65,000 different colors, sampled thousands of times a second for 130,000 antennas. That's why it's such a big data telescope. Once the signals have been separated in frequency, we can process them in the time domain. So stack them together to look for repeating objects like pulsars or one-off bursts. But we can also use them to make images of the sky. We call this image domain data. So we take the signals from each pair of antennas. This is a baseline, and we multiply them together, generating objects that we call visibilities. This is done here for a few signals, but imagine it being done for 130,000 antennas across 65,000 different frequencies. That gets you 8 billion data streams, and it requires around 50 petaflops of dedicated digital signal processing. Once the signals are processed using the dedicated DSP chips, then they're sent off on optical fiber cables to our supercomputers, and there'll be one in Cape Town and then one at the Pawsey Centre in Perth. And the most difficult challenge that we face in SKA is to take the incoming 8 billion visibility data streams and make sense of them. We need models not only of the sky, but also how each antenna was behaving, and even how the atmosphere changed during the data gathering. And we need to operate day in, day out. The science data processes, the supercomputers, are an integral part of the telescopes. If they fall over, we'll probably have to stop observing or at best reschedule. We're constantly trying to keep up with the data that will be pouring in from the receivers. So then once the data leaves the supercomputers, it will be distributed around the world to regional centers. And every year we'll send around 700 petabytes of data around the world. So that's the largest data volume from any scientific facility anywhere. So 24 years after the initial concept, the SKA is an international project now. 16 countries, more than 1,000 engineers, scientists from 270 institutions, spanning the globe across 20 time zones. So let's go another 10 years into the future. And imagine you can stand with me in the West Australian desert. We will be surrounded by 130,000 antennas, spreading out as far as the eye can see, streaming torrents of data through Australia's first mega science project to search for the faint signals of the first stars. I'm looking forward to it. I hope you are too. Thanks very much. And I think we've got some time for questions, Anne. So I'll stop sharing my screen.
Okay, so thank you. And that was fantastic, Sarah. Thank you very much. And I've neglected to say two things at the beginning. One is that this is being recorded so that you can see it afterwards if the people who perhaps weren't able to stay the whole time or weren't able to come online. Start my video, hang on. Right, and if you have questions, could you please put them in the chat or raise your hand electronically. So we have one question. No, that was from Luke. Sorry, I forgot to do that. So please, questions for Sarah. This is an amazing experiment, time domain. It's just unbelievable. So any questions?
And I will say that there are a number of people here who've been playing a role in the SKA for longer than I have, including Anne and Douglas Box. So if I get any particularly difficult questions, I might ask them to answer.
No. Okay, David Hind. Yes, David, please ask your question.
Yeah, Sarah, thank you very much. That was a fantastic talk. I'm just wondering, you emphasised the amount of data that's being generated. What questions is that data going to be focused on? Who's asking the questions, and who will be analysing and trying to get some convergence on what that data is telling us?
Yeah, and so the SKA has a range of what it calls key science projects. And so they range from trying to map that epoch of reionization when the first stars and galaxies started to shine, as I mentioned, to fast spinning pulsars, mapping galaxies, understanding magnetism in the universe. So there are science teams already being established internationally across the world to work out what the telescope needs to look at in order to answer these science questions. And then, so the observatory itself will process the data at first when it's received, but then it will be distributed to those science teams through a network of regional centres. And in Australia, we have a regional centre which is being established now through groups in Western Australia, which will enable the data to be accessed by the astronomers worldwide, and then reprocessed and information extracted from it. So it really is it's a kind of large scale, large team-based approach. There'll also be smaller projects, like individual astronomers will be able to bid for time, but most of the telescope time is likely to go on these large scale sort of projects.
Okay, so I have 3 questions in the chat. The first one, there's so much data coming in, it's an avalanche of data. So the question is, what's the approach to doing the data reduction so that you don't miss rare events?
Yes, and so there are two, as I say, there are kind of 2 main types of data. So the first is data for things that happen once and happen quickly. And there you really want to be very careful that you don't miss anything. So the telescope has triggers that make, so that when it's looking for things, for example, fast radio bursts, and it will trigger and start quickly to save data if it sees something. And then also it will call other telescopes worldwide. So you can see whether you can see them at different wavelengths. The telescope then but also has, much of the sky doesn't change very fast, right? And so in many cases, it's not a question of what are you missing in a time sense, but the question is, the data is so large, how can we be sure that we're finding the interesting things in it? Yeah, we're not going to be able to look through it by hand anymore. And things like AI and machine learning are notoriously good at finding what we already know, but not necessarily so good at finding the new and interesting things. And so this is a real challenge, I think, for astronomers, and one that lots of astronomers are currently thinking about. How do we find what we're not looking for in these enormous streams of data?
Thanks. So we have one question, a live question. John Baxter, do you ask that? And then I've got 2 more in the chat.
My question was, Sarah, you mentioned specifically...
You're too quiet, John.
Microphone on. Sorry, can you hear that now?
No. Something's happened to your microphone. Okay, you'll have to do something because we can't hear you. Let me go to another question. From Adi Patterson, it says, awesome, do we have a sense of what kind of careers young scientists could aspire to?
Yeah, look, I think this is one of the greatest things about having the SKA in Australia, frankly, is that we can inspire our kind of young scientists and our young people towards this. In fact, we employ somebody in our data analysis for the Australian Regional Centre now who says he had a talk about SKA in school and decided he wanted to work on SKA when he grew up, and now he is. And that's why he did science at university, computing. And so that's already, even before we've started building, we've seen that SKA is inspiring scientists in, this person in particular is in Western Australia, but I think probably in Australia as a whole. So there's all sorts of roles that we're going to need. We are going to need maintenance technicians, electricians, and things at site, and then all the way through to big data analysts, astronomers and scientists in Perth and around the world, analysing the data and writing papers. And as we learn how to deal with these enormous torrents of data, I think an interesting thing that we're going to be looking at is how can we share with industry what we learn, and how can we kind of commercialize and spin off so that different disciplines and different sectors can make use of the learnings that we get from what really is very cutting edge in terms of the torrents of data that we're going to be dealing with.
John, do you want to try again?
Can you hear me now? Can you hear me now?
No. Something's, I've no idea because you spoke before. Put it in the chat because I can't hear you. Okay, so next question is, when might we get the first insight into dark matter from John Stocker?
Well, I mean, there's all sorts of telescopes that are looking to try and work out for insights into dark matter, I think, all the time, and not just kind of in the astronomy side, but also the particle physics sort of side is looking at this. So I don't think I can answer that question particularly. What I can tell you is that for SKA, by the time we have built half of the telescope, it will be far the largest radio telescope in the world of its kind. And so we expect to be able to get, to start working with the science community around then. It won't be fully open for science, but with sort of carefully selected teams to start using the telescope and seeing what we can deliver. And so I hope we'll start to see the first science out of SKA kind of in the mid 2020s.
So Trevor Bird has a question. What is limiting our ability to get closer and closer to the Big Bang?
So, well, I mean, so as I mentioned, kind of Planck has already got us really close to the Big Bang. It's actually the time kind of a little bit after that we're really struggling with now. And it's essentially subtracting all the things that are in front of what we want from our data that's the really most difficult part. So there are stars and galaxies, and there is weather, and there is the antenna, the response of the antenna itself and things. And all that calibration is the most difficult bit of trying to get a signal that goes all the way back to that epoch of reionization so that we can try and map that for the very first time. So it takes a lot of staring at the sky from your antennas, and then a really detailed understanding of what you're staring at and what you're subtracting before you can try and get to the background map of the EOR. Have I missed anything there, Anne? I'm going to let you answer some of these questions.
John, do you want to try again?
Okay.
I can't hear you. So, a question from Adi Patterson. Microsatellites. So, how do you? So, in more general terms, how do you avoid satellites, particularly Earth stationary satellites?
Yeah, so look, this is an area that all types of astronomy are looking at the moment. So SKA has a team in headquarters who are talking to some of the satellite providers, very quietly, obviously. It's less of a problem for SKA-Low in Australia because of the frequencies at which the satellites emit than it was likely to be for SKA-Mid, and that it is for optical telescopes. And we know it's a really big problem for some optical telescopes. But still, as the number of satellites goes up and goes up really quickly, it's likely to become more and more of a problem. So I think there are two paths to this. One is working with the satellite providers to say, can we make your satellites so we can see it less? And then the second is trying to work out how we subtract those from our data. And I think that's an area that is getting more and more focused now, but probably still astronomers are not spending enough time and enough effort on this, given the problem that it's likely to be in the future.
I agree, that's a big problem. So we have Ian Opperman has resent his question in a different way. What happens if we see something we're not expecting?
Yeah, we will see things we're not expecting.
So I know that just as a archival story, the Very Large Array, which was the biggest, most powerful radio telescope for a long time in the US, their original science case was very clear and quite detailed, but the things that actually made the biggest impression, none of those were on their science case. So I think this is, yes, there will be unexpected things.
Yeah, and so Hubble Space Telescope is a good example of that. Of the top 10 discoveries from the Hubble, only one was in the science case, right? And so, yeah, we make a good case for our instruments, but I think the main thing is that you make an instrument that opens up the sky so that we can see a new phase space, and then we can see things that we couldn't see before. Yeah, and we don't know what they're going to be. ASCAP is another good example of that. So ASCAP, CSIRO's most recent radio telescope, turns out to be great for detecting fast radio bursts, really fast, some very, very fast radio pulses that come from we're not sure what. When ASCAP was proposed, fast radio bursts hadn't been detected anywhere yet. And so that's a really good example of a telescope, even within its kind of first year, being used to do something new that nobody expected when it was designed.
Great. Now I've seen John's question, which is interesting. So you mentioned what the bandwidth was for ASCAP, but also what the Square Kilometre Array will have. And the question is that to detect atoms other than hydrogen, or is the bandwidth needed for the redshift of hydrogen for the early universe?
Yeah, so it's both of those. Yeah, and so yeah, you need low frequency bandwidths for the redshift of hydrogen, but then higher frequency bandwidths also allow you to detect signals from other atoms and molecules as well. So yeah, it's both.
And here's a question that I don't understand. It says, will the SKA allow us to look at block universe theory flow of the time?
Yeah, I don't understand that one either.
I don't know what that one means, sorry. And besides, I think we're now very close. So unless there are any burning questions, I think we might pull this to close. And I would like to make a vote of thanks to Sarah. I mean, this topic is clearly very close to my heart. I'm an astronomer, and I am continually amazed by the scale and complexity of this project. So the numbers involved, huge numbers of antennas, tsunamis of data through many, many kilometres of optic fibre, the potential to look back to the earliest time in the universe, and the massive number of unexpected discoveries. They're all truly gobsmacking. So Sarah, you're charged with leading the Australian project, and tonight you've given us a taste of the challenges and the opportunities for the future, particularly for the next generation students. So we'll watch with awe as the telescope is constructed, and we wish you every success. Thank you for sharing your vision and your insights tonight. So thank you everybody. I think that ends the session. Thank you to Mitch for the technical support, for everyone who's attending, especially thank you again, Sarah. And keep safe and have a good evening.
Thank you, Anne, and thank you very much for everybody for the opportunity to chat to you. It was good.